Okay, let's jump right into Chapter 16, Conjugation, Resonance, and Dienes. First, a few definitions. Conjugation. Conjugation is the overlap of unhybridized p orbitals on three or more adjacent atoms. Often we have 1,3 dienes. Now, 1,3 diene, well, ene is double bond, diene means two double bonds, 1,3 means the first double bond is on carbon 1, the second double bond starts on carbon 3. So here's 1, 2, 3, a 1,3 diene. This is 1,3 butadiene, buta because there are 4 carbons, and chemistry makes sense. All right. Note, if we look at the hybridization of each of these carbons, all three of them are sp2 hybridized, which means they have an unhybridized p orbital. Since they're sp2 hybridized, all 4 carbons are trigonal planar. And if we look at that unhybridized p orbital, note we've got the sigma bond between the first 2 carbons here, the sigma bond between the last 2, the sigma bond in between these 2, and then we have the pi bond here and the pi bond here. But the question is, if we have an unhybridized p orbital on this carbon and an unhybridized p orbital on the third carbon, can't we get a pi bond there? Can't we get overlap between an unhybridized p and an unhybridized p here and get a pi bond there? We are going to look at that further. The truth is we can kind of see that you can get some overlap there, and that's going to affect the properties of these. Note, this is a conjugated system represented by alternating double single bonds. Double, single, double. That's a conjugated system. This is an isolated. Double, single, single, double. Nope, no conjugation there. Note, you can also get conjugation through allylic carbocations. If we have a CH2, double bond CH, we note the carbon next to a carbon of a double bond is the allylic position. And if you have an allylic carbocation, we can also get some conjugation. We'll look at that further in the future. But the first thing to look at is resonance, because when we have complicated situations that are a little difficult to understand, for example, why don't we get a good double bond here? It looks like we should. Why don't we get a double bond here? Often resonance is a nice way to look at it. So let's go into resonance. Note, this is a review of a little bit organic 1, Gen Chem 1. All right, so let's start by looking at those allylic carbocations, the one we had here. All right, so note that if we have this allylic carbocation, it has a resonance form. Recall, with resonance forms, you can move electrons, but not atoms. Or another way of saying it, we can move pi electrons, the pi bonding electrons. We can move lone pair electrons, but we cannot move sigma bonding electrons. We cannot break single bonds, because that would be breaking an atom off. So if we have this, we want to draw a resonance form. Recall the arrow here for resonance. We say, okay, well, what can we move? Well, we can move the pi bonding electrons. Well, let's move the pi bonding electrons over to here to make a double bond here, and then we find our positive charges on this carbon over here. So we have that, and that's the resonance form. Note, we didn't rotate the molecule. For example, what if this were a carbon 13? Here in this resonance form, the carbon 13 is double bonded. In this resonance form, the first carbon being carbon 13 is the carbocation. So we didn't move any atoms, we didn't rotate the molecule, we just moved the electrons around. And note, whenever you can do that, just move electrons around, you've got resonance forms. And the thing to remember, very important, is it's not that these two forms are switching between each other. That's not what is happening at all. It turns out the real thing that's floating in solution, the real molecule, is the resonance hybrid. It is the combination of it. This thing right here, the resonance hybrid, is the thing that's really floating around in solution. This bond here between these two carbons, it's not a double bond, it's not a single bond, it's somewhere in between a double and single bond. Same with the one on the other side. This carbon is carrying partial positive charge. This one's carrying partial positive charge in the resonance hybrid. But 100% of the time, this is the thing that's floating around in solution. 100% of the time, allylic carbocations look like this. They are not bouncing back and forth between these two. No, that is not what is happening at all. 100% of the time, they look like that. We tend to draw them like this because we don't want to draw them like this all the time. So one thing to remember with these structures, when we see a structure, we have to recognize, oh, this has resonance, and we have to recognize what it means, even if we only draw one of the structures. And the other thing to remember is when you move electrons around, when you have resonance forms, that means that the electrons are delocalized. The electron density and charge are delocalized, and that's the way molecules like it. So delocalizing the electrons and the charge means the resonance hybrid is lower in energy than any one resonance form. If you calculated the energy of this molecule without resonance compared to the energy of this one, you'd find the energy of the resonance hybrid is lower in energy. And this is very important. When you see resonance, that means that molecule is more stable than you think it should be. Resonance means stability, and we're going to find out that that's a driving force for a lot of reactions. If your product of your reaction can have resonance forms, that means it's more likely to form than you think it should. All right, and when it comes to carbocations, this resonance also gives us our carbocation stability. Recall the methyl carbocation, very, very unstable. Primary carbocations aren't very stable at all. Secondary are more stable, and secondary are about the same stability as allylic carbocations. Allylic carbocations have about the same stability as secondary carbocations. And you'd say, wait, but isn't this primary? Isn't this positive charge on this primary carbon here? No, it's allylic, and due to this resonance, it means this beast is more stable than you think it would be. So this carbocation is much more stable than a primary, even though it looks primary. It's allylic, so it's about as stable as a secondary carbocation. All right, cool. So if we have a couple of molecules here, down here, could you draw the resonance form of this molecule here? I see this carbocation. What's the resonance form? Well, we see, okay, carbocation here, double bond. Well, that's an allylic. Double bond, single bond to a carbocation, that's an allylic, which means we can move the double bond over here and the positive charge up there, and we can make that. Note, very important, that realize that we only have one hydrogen on this carbon. Don't go making two hydrogens on this carbon. You can't move the positive charge over here because this has two hydrogens over here. So you can't just swing it to the other side through resonance. Because there's two hydrogens here, to have a carbocation, there could only be one hydrogen, and you'd have to break one of these hydrogens off, and you can't do that with resonance forms. All right, cool. And of course, when we see this, we realize a resonance hybrid really looks like this. We've got partial double bonds between the carbon in this one and this carbon over here, and partial positives there. Okay. Let's look at some common resonance. Instead of having to work out resonance forms every time, let's just look at resonance that we just commonly see so you can recognize it. As we just saw, an allylic system, a double bond followed by another atom at the allylic position. And as long as atom Z here, this allylic carbon, has a p orbital, it is sp2 hybridized or sp hybridized. As long as it's not sp3 hybridized, then we're having an allylic system. And so this can be a carbocation, it can be an allylic radical, it can be a carbanion. All of those things let us have resonance. An allylic system where this position here, the allylic position, is sp2 hybridized. It has at least one unhybridized p orbital. All right. All right, conjugated double bonds, especially in aromatic systems. Note we have a double bond, single bond, double bond, single bond, double bond. Note we can move this double bond here, and this one here, and this one up here. So benzene is an example. Aromatic systems are resonance. One would look at them as having these two resonance forms here. We'll look at more aromatic systems in the next chapter. Okay. Note, here's our 1,3-butadiene. Note that it has a resonance form. If we could move the double bond between these two, we were wondering earlier if we could, but if we move the double bond between these two carbons, that means this double bond would have to break and would have a lone pair on this carbon, making it a carbanion. Positive charge here, carbocation. But note, this also has a resonance form. If we just made the arrows go the other way, we would get this beast down here. So there's actually 3 resonance forms here. And something that you may remember from Gen Chem 1, not all resonance structures are equal. Because we have this form here where everything has its octet and there's no charge. When we look at this beast here, this carbon here does not have its octet, and we've got charges here. So we know this resonance form is higher in energy than this resonance form, as is this one down here. However, the truth of the matter is we do have a resonance hybrid because of these 2 resonance forms, which means this molecule, because it has resonance forms, is a little more stable than you think it would be. All right. Other common resonance, when you have a lone pair on one atom and a carbocation or positive charge on the adjacent atom. So if I have a lone pair here and a positive here, we can just form a double bond between those and move the positive charge. Here's an example here. We've got an oxygen with 2 lone pairs on it bonded to a carbocation. You could form a double bond here. And now the oxygen carries a positive charge. All we did was move electrons around, so that is an example of resonance. All right. When you have a double bond between 2 different atoms, the more electronegative atom just might take those 2 electrons. We can break this pi bond and put the 2 electrons on the more electronegative atom. That is a common resonance. And we can see that here. Here's carbon double bond oxygen. Break the pi bond, make a negative charge oxygen, a positive charge carbon. So we have resonance forms here. And so here's a little exercise to do on your own. Draw 2 resonance forms for this. Here's the answer. I want to pause the video and work on the problem before looking at the answer. It's really up to you, eh? Okay. Note, the resonance hybrid, as we just mentioned, more closely resembles the most stable resonance structure. All right. So, when we looked at, let's go back 2 pages. When we looked at this resonance here, note this resonance form here looks like we just flipped the molecule. We noted how we didn't. We moved electrons and the positive charge around. But if it looks like all we did was turn the molecule around, that means these 2 resonance forms have the same energy. Therefore, if these 2 have the same energy, the resonance hybrid is an equal average, one might say, of these 2. The real molecule kind of looks like the average of these 2 because we only have 2 resonance forms and they are equal. However, when we looked at our butadiene, here we can see that this form is not equal to these. We've got charges here, and we recall with resonance forms you don't want charges. We don't have our octet here, which means these 2 resonance forms are higher in energy than this one, which means the resonance hybrid more closely looks like this. If we were to draw the resonance hybrid of this 1,3-butadiene here, we would find that these 2 carbons, there's pretty much a double bond. It's just a little bit longer than a normal double bond. A little bit longer than a normal double bond here. And what we'll also notice is this bond in between these 2 carbons is just slightly shorter than a single bond should be. Because we have these 2 resonance forms, and they do have double bond in between those 2 carbons, it is just a little bit shorter. All right. Other rules for determining what's the more stable resonance form. Um, More bonds and fewer charges, more stable. Every atom having its octet is more stable, which leads to something that seems a little crazy. What is more stable? This with the oxygen having two lone pairs and us having a carbocation, or this being a H2 double bonded to this oxygen with one lone pair and the oxygen being positively charged. Now, normally you would think, ooh, oxygen, a positive charge on the more electronegative atom, that's not good. But the fact of the matter is, this carbon does not have its octet. This carbon has its octet, the oxygen has its octet, this carbon does not have an octet. Here, this carbon has the octet, the oxygen does have an octet, and now this carbon has an octet. Therefore, this is actually the more stable resonance form. Even though we've got the positive charge on the more electronegative atom, which doesn't seem good, everything has its octet, so this is the more stable resonance form. All right. Normally, though, we do want the negative charge on the more electronegative atom. Therefore, if we look at these two resonance forms, would we rather have a carbanion or this oxide here, this oxygen with the negative charge? This is a more stable resonance form here. It's more stable to have the oxygen have the negative charge compared to a carbon. And note, we don't have to worry about octets because in both of these resonance forms, all three carbons and the oxygen have their octet in both of them. So we don't have to worry about octet issues with this one. Therefore, if we're not worrying about octet issues, the oxygen, the more electronegative atom having the negative charge, is the better resonance structure. Here, we can give oxygen the positive charge, even though it's more electronegative, because everything has its octet here. All right. So, last thing, pretty important, if resonance shows electron delocalization, that means the atoms must be sp2 hybridized, and therefore they have trigonal planar geometry. All right, so that's enough for this video. We will continue on with the next one, looking at conjugated diene stuff.